Hello, everyone. Thank you very much for coming to Rio and to IMPA. So I hope that everything is okay. Physics is well known to be an area which is not accessible by people outside, whereas number theory is well known for its problem, which is access, which you can understand even when you are high school students. And we hope that this mixture will produce more excitement. It has already produced many excitements. So let's start our first week. Since this is our first experience, you can send comments, suggestions, complaints to the email NET School, or you can talk with Giulio, Emmanuel, and the other organizers. And yeah, so maybe let's see.
Okay. Giulio. Yeah, so I welcome all of you to come to Rio. It's a great pleasure to have all of you here. And I think it's a very important moment for mathematics in Brazil. And it's also a very important moment for number theory. So now here we are in Brazil and we'll be talking about number theory. And I hope all of you enjoy. It's with great pleasure that I want to introduce our first speaker, who is Professor Steve Gonek from University of Rochester. And he will speak about a motivated introduction to the theory of the Riemann Zeta-Function. Thank you.
Thank you. Well, I want to thank the organizers for inviting me. This is my first time in Brazil, and it's a great opportunity for me to see Rio, which looks spectacular from the little I've seen so far, and to see IMPA. So thank you. I'm going to talk today about an overview of the subject of the Riemann Zeta function, and my idea was to give you an idea of what the subject's about, touch at least on a lot of different important problems and results, and but not prove much in the first talk and a half. Later, starting with the second half of the talk after this, I'll give you some basic proofs. What I wanted to do was give you a clear indication of the growth of the subject of the zeta function, the theory, and motivate it so you could see why it grew and how it grew naturally, and what some of the big problems were that led to that growth. So that's what I'll do, and I'll start with a little bit of history, and it really begins with Euler. Let's see. Okay. Let me just get oriented here. Okay, so here's prehistory of the zeta function. Around 1740, Euler observed that the sum n to the minus sigma, which is a function he had worked with before, has this Euler product representation. And you can see that because the product in the middle of that line can be expanded. It's the sum of a geometric series. And if you multiply out the series, you get a collection of terms that look like this. Arbitrary powers, integer powers of positive integer powers of primes. raised to the sigma. And every one of those is of the form n to the minus sigma. So you certainly produce every term in the sum that we started with. But also every term comes just once. And that's a consequence of the fundamental theorem of arithmetic, the part of it that says factorization into primes is unique. Okay, so this was his starting point, and it's the starting point of analytic number theory. Now, one thing I've already slightly misrepresented what Euler was doing, because for him, sigma was basically an integer. So in the paper where he proves, gives his proof of an infinite number of primes, in fact, sigma is 1. So it's a little peculiar, so I'm reinterpreting this. It was Dirichlet who really started to work with this in the 1830s or thereabouts, who looked at sigma as a real variable. Okay, so using this identity between the product and the sum, Euler gave another proof of Euclid's theorem that there are an infinite number of primes. So this is recast. This is not how it looks in Euler's paper. But in modern terminology, if there aren't an infinite number of primes, then zeta of sigma is this finite product. And if you let sigma go to 1, the result is finite. But we have an expression as an infinite sum, and we know that that sum goes to infinity as sigma goes to 1 from the right. So you have a contradiction. So there must be an infinite number of primes. Okay, so many of you may have seen all of this before, but I want to point it out because it illustrates a fundamental theme of the whole subject, namely that the behavior of the zeta function is intimately connected. There's this double arrow here has a precise technical meaning. It's intimately connected with the behavior of the primes. Okay. The next step in this progression here is that of Gauss and Legendre. Empirically, they decided that the number of primes up to x is about x over log x. This is strictly an empirical observation that they did by looking at tables of primes. And we call this the prime number theorem today. Pi of x is the sum p less than or equal to x, and that should be asymptotic to x over log x. Asymptotic, I'm not sure what kind of notation various people with different backgrounds have. So I'll just tell you this means pi of x divided by x over log x tends to a limit 1 as x goes to infinity. Another way to write this that's equivalent, and that is we'll see later, is if you let lambda of n be log p if n is p to the k for some positive integer k, and otherwise 0. So you're counting primes and prime powers with weight log p, then this function psi of x is some lambda of n. That's its definition. And the prime number theorem is equivalent to that being asymptotic to x. So if you're not used to this, just a way to think about this is that psi of x is essentially the sum log p less than or equal to x. Now in that sum I've left out p squares, p cubes, and so on, but as a simple exercise you can show that that contributes not much. So square root of x log x, in fact, at most. So you have that, but over most of the range p less than or equal to x, most of the range is, say, between x to the 1 minus epsilon and x. Log p is log x, roughly. So this should be log x times the sum 1. So that's pi of x times log x. So just some way to think about these things if you're not used to this. The next big development was by Chebyshev around 1850. And Chebyshev proved two very nice theorems. The first was that he showed that if this limit, pi of x divided by x over log x exists, then it's got to be 1. So if there is a limit, and that's actually the difficult part, then the prime number theorem is true. And the second result was that he showed that pi of x is of order x over log x, that he got the correct order of magnitude bounds above and below for pi. In fact, he was concerned about these constants and got reasonably good constants for the time that allowed him to prove from this result here that Bertrand's postulate is true, namely that between x and 2x there's always a prime. I guess x has to be at least 2, depending on how you want to count it. But okay, so that's the history of our subject up to, apart from Dirichlet. Dirichlet proved the prime number theorem, not the prime number theorem, but he proved that there are an infinite number of primes in arithmetic progressions. So I've left that out. That's a glaring omission, but so be it. Then the next big result was Riemann's paper in 1859, 1860. So I want to go through some of what he did in detail because this paper was pivotal in the subject. It really created the modern theory of the zeta function, and it served as a roadmap for the work of the next 50 to 100 years. I mean, depending on how you look at it. Certainly the first 50 years after it. So the paper is called On the Number of Primes Less Than a Given Magnitude. It's very short, but there's a lot of stuff in it. And one take on what Riemann is doing is he's showing why the prime number theorem is true. So, I mean, that's just one way to cast it. And this, to my mind, is remarkable because, you know, you have this statistical law about pi of x, and, you know, you have a statistical law. Why should there be any reason? I mean, in a lot of mathematics, when you have a statistical law, it's not, you know, it's hard to say why it really should be true. But Riemann somehow gives us a connection of the primes to the zeros of the zeta function that shows why such a statistical law is there. So Riemann starts with the equality between the Euler product and the sum n to the minus s. And this is for a real part of s bigger than 1. So s now is going to be a complex variable. And this is a big innovation of Riemann. It's very, very important. He's brought to bear what was then the modern theory of complex variables, function theory, on this subject. So he calls this zeta of s. I'm not sure. This may be the first place where the zeta function is called zeta of s. But he certainly calls it that. And he proves two or three things in his paper, and he conjectures some other things. So let's go through them. The first is he shows that zeta of s has an analytic continuation to the whole complex plane, except for a simple pole at s equals 1. Okay, so the series at the start of this here and this product, they are absolutely convergent to the right of 1. So the zeta function initially lives simply in that half plane, real part s bigger than 1. But Riemann extends this. This is all part of his general philosophy of a global view of theory of functions. He extends this to the whole complex plane. And then he shows that it has zeros in the half plane, real part of s less than 0, that are simple. They're at the negative even integers. Let's see. And these are simple zeros, as I've said. And these we call the trivial zeros. Often they don't play much of a role in the theory of prime numbers and arithmetical questions. Sometimes they do. Second thing he proves in two ways is that the zeta function has a functional equation. And it looks like this. There are many ways to cast it, mostly because the gamma function satisfies various relations. And so you can use that to rewrite things. So this shows a symmetry between S and 1 minus S. Okay, so that's one form of functional equation. Another is if you collect all the gammas and pi's on one side and write that as chi of S, then zeta is chi of S times zeta of 1 minus S. And one thing to think about is that chi here, being a quotient of well-understood functions like gamma and powers of pi, is basically known. There's not much mystery there. Okay, then he argues for various things that he can't completely prove. And partly that's because the science hadn't caught up, the techniques hadn't caught up with where Riemann was. So he asserts that zeta has infinitely many zeros besides the trivial ones that we refer to as rho equals beta plus I gamma, and they're in the critical strip. That's a strip of the complex plane where sigma is between 0 and 1. And then the functional equation, there was a symmetry, S to 1 minus S. That tells you that if you have a 0 in the strip to the right of a half, then you have one to the left of a half at the same height. And then the zeta function also is real on the real axis, so from that you deduce that a complex conjugate of a 0 is also a 0. So if you have 1 0 off the line, you have the critical line, sigma equals a half, the one down the middle, then you have 4. Okay, he also says that the count for the number of non-trivial zeros up to height t in the critical strip looks like this. Okay, there's some ambiguity about this error term, but essentially one reading is that this is what he's saying. Then he says that if you define a function xi of S, and this is this from here, the pi on is the expression you saw in the functional equation on the previous slide. You multiply that by a half s minus 1. So this s minus 1 kills the pole of the zeta function at 1. Then this is an entire function. And he further asserts that as an entire function, you can factor it over its zeros, just like you can a polynomial over its zeros, and you get a factorization like this. Okay, here again, his intuition was quite good. He knew what he was talking about, but the techniques for proving something like this rigorously weren't around at the time. Okay. He also gives an explicit formula for pi of x. Now, I'm writing it because it's less complicated to write it for psi of x. I'm writing it that way. It turns out he also had a formula, this formula too, for psi, but it's not in the paper. So lambda of n is this function that's log p at the powers of a prime. And the explicit formula, now there are many explicit formulas, but this is sort of a prototype. They're mostly quite similar in some basic respects. But he says that if you sum lambda of n, which is the expression we want to show is asymptotic to x in the prime number theorem, that this is x minus a sum over the non-trivial zeros of the zeta function plus a sum over the trivial zeros of the zeta function minus a constant. Okay, now from this, so remember, this isn't quite in the paper, but something like it. From this, you can basically see why the prime number theorem should be true. Okay, now he didn't prove the prime number theorem, but he sketches what's going on, what's really behind it. So why should the prime number theorem be true, that psi of x should be asymptotic to x? Well, this is a constant. If x is large, this is small, this sum. Okay, so you can ignore those. And then everything comes down to this sum over the non-trivial zeros in the critical strip. Now, the rows are beta plus I gamma. And Riemann says that the betas are less than or equal to 1. If the betas are less than 1, then maybe, now it's an infinite sum, but if you disregard that, so if the betas are all strictly less than 1, then the absolute value of these terms is x to the beta, so x to something slightly less than 1 over rho. There's a chance that that has order little o of x. Okay? It's not clear from this, but it's highly suggestive. And that's why the prime number theorem should be true. Yes? So, I'm sorry.
How do we see this formula? Is that an easy formula?
I will show you later in another lecture. Okay, yeah. It's not that difficult. Once everything is, once you've proved enough details, like the size of the zeta function and so on. Okay, and then finally, the last thing he conjectured, well, I don't know the order, I don't remember, but his famous conjecture is that all the zeros in the critical strip, the non-trivial zeros, have real part 1/2. Okay. We don't know how he came up with this conjecture. We do know that he calculated some zeros. This wasn't brought to light until the 1930s in a paper of Ziegel's. He actually calculated the first few zeros, and they were on the critical line. Okay, so that's what Riemann did in that paper, and that kind of set the agenda for the next 45, 50 years. Okay, and here's what happened afterwards. So in 1893, so remember Riemann's paper is 1859, 60, Hadamard proved this product formula that Riemann asserted, that Xi, this entire function, factors over its zeros. And this was a consequence of a lot of the work that Hadamard did in his thesis on entire functions. Okay, so he had developed the theory rigorously enough to do this. And in order to prove something like this, if you know a little bit about Hadamard factorization of entire functions, you have to have some idea of the density of zeros. And Hadamard proves that n of t is less and less than t log t. Then in 1895, von Mengelt proved this explicit formula. Okay. And then the next year, Hadamard and Della Poisson independently proved the prime number theorem. And to do that, they needed to know that zeta of 1 plus it never vanishes. Okay? And they both had to give proofs of that. Then, 1899, Della Poisson proved the prime number theorem with error term. So, prime number theorem initially said that psi of x is asymptotic to x. Prime number theorem with error term means that psi of x is x plus something of smaller order. And to do this, he needed to prove a zero-free region for the zeta function. What this means is he needed to know not only are there not zeros on the one line, but that there aren't zeros of the zeta function too close to the one line. So this is called a zero-free region. And then in 1905, von Mangold proved this formula that Riemann gave for the counting function of the zeros in the strip up to height t. Okay. So you see all these claims of Riemann were eventually proved, except for the Riemann hypothesis. Okay, so if we look at the explicit formula, actually I can teach you a basic lesson of the subject that could carry you a long, long way, and that is the explicit formula. And remember, there are many, so the explicit formulas are everything. Okay? It's a good thing to keep in mind. So this explicit formula, and we saw how to get the prime number theorem from this. This brings out another basic point in the subject, namely that the distributions of the zeros of the zeta function, so this term here, this all-important term, their distribution, we needed to know, are there any on the line? Can we keep them away from to the left of the one line? That's intimately connected to the distribution of primes, okay? So before, from Euler's result, I said behavior of zeta as a function is intimately connected with the distribution of primes, and now we see more specifically distribution of zeros of zeta. Not only that, but this is one important property of the zeta function, is intimately connected with the distribution of primes. Okay. This brings up a crucial point in the whole theory, to my mind. The distribution of zeros of an analytic function is closely connected to the size of the function. Okay? You want to know about the distribution of zeros? It would be good to know about the size of the function in regions. Okay? And this basic idea led, I think, to a lot of the growth of the subject. So what is this connection precisely? Well, here's a formula that you often learn in a first course, in a graduate course in complex variables. Maybe many of you have seen it. This is Jensens Formula. And it says if you have an analytic function in a disk, a radius r, and I've written it so that it's centered at the origin, but you just can modify it so it can be centered anywhere. You want the function not to vanish at the center. And if z1 through zn are all the zeros of f in the disk, then the log of this quotient, so the radius to the n, radius of the disk, divided by the product of the moduli of the zeros, is the average of the log of the function minus the log at the center. Okay, so how do you interpret this? Suppose that you look at some disk and you got a bunch of zeros inside, and let's imagine that the disk, we take the radius large enough so that it's not, none of the zeros is too close to the perimeter. Then this side will be, well, let's say all the z's are in fact no bigger than r over 2 in modulus. All right, then this side is going to be, 2 to the n. Log of 2 to the n is n log 2 at most. And here you have a bound. Let's say you know the size of f, so you take the log, integrate, so on. I mean, you estimate this. And then a bound for f translates into a bound for n. So you can't have too many zeros if f isn't too big. Okay, now Dirichlet series, unlike power series, live naturally on half planes rather than disks. So there's a version of this that is mostly used for analytic number theory, and it looks like this. It's due to Littlewood. And The principle is the same, but let's go through it. I'll actually give you a kind of proof of this in another lecture. But if f is analytic on a rectangle, and the left edge goes from sigma to sigma plus it, and the zeros inside the rectangle of f look like this, then the sum of the distances of the zeros to the left edge, okay, that's what this is. So you take the zeros inside the rectangle, you add up their distances to the left edge of the rectangle. That's equal to minus 1 over 2 pi I times the integral of the log of f around the rectangle. Okay? If you know how to prove, well, I shouldn't say that. I was going to say if you know a proof of Jensens Formula, you can prove this, but it sort of depends on the proof you choose. But whenever I mention Littlewood's lemma, I'd like you from now on to think of it this way. So as the integral of log mod f on the left edge of the rectangle plus an error term. In applications, this error term is usually something we can ignore. It's of lower order. So if you think that way, it'll help you in some of the arguments you see later. Okay, so the size of zeta tells you about the distribution of its zeros, and that in turn tells you about the distribution of primes. So how do you measure the size of zeta? Well, there are many ways, but two of the most important turn out to be pointwise bounds, naturally enough, and estimates for that are called order estimates, and mean values of zeta on vertical lines, okay, or sometimes called moments. So they look like this, okay, and sigma is generally anything from a half to the right. Okay, now, so my point here is that estimates for these two kinds of objects have sort of determined the growth of the subject in certain directions. Okay, these are very important, and later when Brian Connery and John Keating speak, they will touch on problems like this of both types, and so you can see ultimately where these problems come from is the distribution of primes, and other arithmetical questions too that I'm not talking about today. Okay, so after the proofs in Riemann, of Riemann's assertions, there was this development of finding the order of the zeta function, and these are still unsettled questions. We know many more things than we used to know not long ago, but these are still wide open problems ultimately. Okay, so let me talk a little bit about the order problem. Again, I'm not going to prove anything, but just describe what's known. So I'll split this into two pieces. The order of the zeta function near the one line, and then the order inside the critical strip. And remember, the functional equation gives you a symmetry around the 1/2 line in the critical strip. So you don't really need to think about order and moments to the left of a half. Okay, so near the one line, how big can the zeta function be? Okay, now there's extra motivation for this in terms of primes. Good upper bounds on the one line or near it give you good zero-free regions, which you saw were useful in proving the prime number theorem. Okay, and the better the zero-free region, the better the error term. Okay, so what's known? Well, Littlewood in 1922 proved that zeta of 1 plus it is less and less than log t over log t. And this translates into an error term in the prime number theorem that's a little better than the one Delaval Poisson had. He had this without the log x. So this is a slightly better error term. Okay, and then in 1958, Vinogradov and Korobov independently were able to shave the power off of the log, made it log to the 2/3. This used very deep and complicated methods of exponential sums. And that led to an error term in the prime number theorem, which is still essentially the best one we know unconditionally. That means, unconditionally means not assuming something like the Riemann hypothesis. And it looks like this. So instead of square root of log x, you can put a log x to the 3/5 here. So that's better. Okay, now this brings up a question. If you're studying the size of the zeta function in the critical strip or on the one line, and the zeta function lives initially, this infinite sum or product, or to the right, they exist to the right of 1, and you want to go to the left of 1, how are you going to do that? Well, you need some sort of approximation, and so I just want to take a minute to tell you about the approximate functional equation. There are many ways to approximate the zeta function inside the critical strip, and the most generally used one is this, the approximate functional equation. This was proved by Hardy and Littlewood around 1918, if I'm not mistaken. But it turns out that Riemann knew much more precise results than this way back. But this is one version. This is a very specific version of the thing. But it says that zeta of S can be written inside the critical strip as a partial sum of its infinite sum, that we had to the right of 1, plus chi, this is the factor from the functional equation, times another truncation of the zeta function, but this time at 1 minus s. And then there's a reasonably good error term here. Okay? So using that, you can get hold of the zeta function inside the critical strip. That's often how you do it. Okay, now, so how can you prove estimates using that, the approximate functional equation, inside the strip? Well, so we have zeta of S looks like this, and I'm writing E for an error term. It's different every time you see it, probably. So now the point is, you take these sums and you take sections of them. They look like this. This is of the form n to the minus sigma, you can think of as g of n. E to the minus I f of n is e to the minus I t log n. So f of n is t log n. And then using a whole science and art called exponential sum methods, you can try to get hold of the cancellation in sums like this. So instead of just putting absolute values around terms and adding, you try to make use of cancellation of the individual terms. So one thing I'm just touching on but will skip for the most part is that, well, it's 2 chapters in Titchmarsh. There are the methods of van der Korpet and Weil, and then a later method of Vinogradov on exponential sums. And these are methods you use to treat these things, and I won't say anything else about them. Okay, so that's what Littlewood did. That's what everybody else has done. Vinogradov and Korobov used Vinogradov's method of estimating exponential sums to get his result. Okay, so if you have estimates like this, you want to know what's the truth, though. Okay, are you close? And usually when we ask such questions in difficult problems, and this is a difficult problem, we don't really know, but we have ways of guessing. So what we do know is that the limb sup of zeta divided by log t is less than or equal to twice e to the gamma. Gamma is Euler's constant. we can prove that if you assume RH. This was proved by Littlewood. And so for those of, I don't know, do physicists, how many of you are physicists? Do you talk about limb soup in? Okay, so just think of it as zeta of 1 plus IT is never more than this constant plus epsilon times log t. Okay? And then we also know, and now this is unconditional, this lower bound, that the limb soup is bigger than or equal to e to the gamma. So here's a 2e to the gamma, here's an e to the gamma. Okay, and let me translate the limb soup. This means zeta on the one line at height t is, something, yeah, okay. So what this means is that infinitely often in t, going to infinity, zeta of 1 plus it is bigger than or equal to e to the gamma minus epsilon, any positive epsilon, times log t. Okay, so the order of zeta could get very, very small, but infinitely often it does get as big as a constant log t, and we expect, but we don't have a proof of this, except on RH, that it doesn't get bigger than log t. Okay, so if we look at the best proven results on the upper bound, you get log to the 2/3 of t here. What we really think is that it should be log of t. Okay. This is a big question. This, well, first of all, proving a really good bound, something better than that, but something like this, it would be incredible. But even here, if you assume RH so that you have just a 2 difference in the upper and lower bound, that's a very deep problem. Okay? And people have been arguing about that for many years. Is it closer to the 1? Is it closer to the 2? Or is it 3/2? Okay, so how are we doing? Okay, so now let's move deeper into the, yes? Well, you would think so, except that log grows very, 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 very slowly. In fact, yeah, it's so unfortunately we don't have good numerical ways to check. We don't know the constant. You've got a log as opposed to a log, and you've got constants that we don't know. Okay, so now we're moving inside the critical strip between 1/2 and 1. So here it's helpful to describe something called the Lindelof mu function. For a fixed sigma, mu denotes the greatest lower bound of the numbers xi for which this inequality is true, that you can bound zeta. So any xi such that 1 plus t to the xi bounds zeta for, if you can find some constant in this less and less and that works, then the greatest lower bound of such x's is mu of sigma. So you fix a sigma and then you find the bound. So this is how we measure the order of zeta inside the strip. Zeta has an absolutely convergent series to the right of 1. So if you imagine a fixed sigma bigger than 1, zeta is bounded, and therefore the xi here, any xi bigger than or equal to 0 is going to work. And you can also show mu is not negative. So mu of sigma to the right of 1 is 0. Okay? Okay, what about in the strip? Well, to the left of the half line, because of the functional equation, to the left of the half line, you know the growth of zeta if you know it to the right. Oops. Okay, and so if you look at sigma to the left of 0, by the functional equation, zeta is chi times zeta of 1 minus s. If sigma is less than 0, 1 minus sigma is bigger than 1, so zeta is bounded. Chi is about t to the half minus sigma for large T in a strip. So the growth of zeta to the left of 0 looks like this, and that means that mu of sigma is a half minus sigma. You can show it's got to be exactly that. Okay, and Lindelof showed that mu is a continuous function. It's the same circle of ideas as in the Fragment-Lindelof theorems from complex variables. Mu of sigma is continuous, it's non-increasing, and it's a convex function. Okay, so here's a picture of what I was just saying. Here's mu to the right of 1, here's mu to the left of 0. Because mu is convex, it must lie below this dotted line in the critical strip. Okay? If you look at the sigma equals a half, then this point above it is 1/4 on this line. So zeta shouldn't be bigger than t to the 1/4 plus epsilon on the critical line. Okay, and that's called the convexity bound. So I'm throwing out a term like that because that's a very important notion these days, and you may hear it later. Convexity estimates for L functions. By the way, I'm talking just about the zeta function, but the problems and the methods that are used here carry over to a large extent, not entirely, in other contexts for other L functions. Okay? So it's not as specific as I'm making it seem. Okay, improving this convexity bound, getting below t to the 1/4 for zeta on the half line, is another really important and problem that has lots of applications. So here's a bit of the history of that problem. Hardy and Littlewood showed that t to the 1/6 plus epsilon is admissible. They used Hermann Weil's method, what was then a relatively new method of exponential sum estimates. And then there's a long list of people over the next 90 years who made improvements, and I couldn't possibly put everyone down there. But the best result until recently was by Martin Huxley. He had mu of a half is less than 0.15609. So that's, you shaved off the, that second digit. In 2014, Bourgain announced a small improvement on this, but, small improvements are not small efforts, should be known. Okay, so what's the truth about mu? Well, we believe the Lindelof hypothesis, many of us believe this, and it says that mu of sigma is not only 0 to the right of 1, but to the right of a half and greater. Okay? That's called the Lindelof hypothesis. And here's a graph. If you believe the Lindelof hypothesis, that completely determines what the mu function looks like. And it looks like this. Okay, the line I had before was a dotted line here in the critical strip between 1/2 and 1. Okay. All right, so that's the Lindelof hypothesis. And that translates into log mod zeta being less than or equal to epsilon times log t, right? So mod zeta is less than t to the epsilon for any epsilon. Okay, what's the truth here? On RH, we know, and I'll give you a proof of this in a couple of days, we know that log mod zeta is bounded by log t over log t, assuming the Riemann hypothesis. The best result we know without any assumptions for this upper bound is log t. And then for lower bound, infinitely often log mod zeta gets as big as square root of this, square root log t over log t. Okay? Now this difference between square root and not a square root, is a reflection of that 1 or 2 problem. And by the way, the lower bound is due to Montgomery on RH, and then Balasubramanian and Ramachandra unconditionally. So the lower bound, whether the lower bound or the upper bound is closer to the truth is intimately connected with that 1 or 2 problem that we saw for how big zeta is on the one line. All right, so now that brings me to the moment problem. Let's see how we're doing. Okay, what do I have like? Oh, okay. Try not to use that. I think we all need coffee. Okay, so let me talk about moments now. So that's what we know about order results. What about the moments of the zeta function? So you're going to hear a lot about this week. So I'll just try to give you a basic background. So these moments are, they're related to the distribution of the zeros. And here's some of the things I'll show you tomorrow that they're used for. So zero density estimates. And those are estimates for the number of zeros in the critical strip. So let's say, so here's 0, here's 1/2. Pick a sigma between 1/2 and 1, and count up, go up to height t. And how many zeros are in this box? Okay. Now, the Riemann hypothesis says there's no zeros here once you move to the right of 1/2. Okay? Well, zero density estimates tell us, if there are zeros, remember the number of zeros up to height t in the critical strip is t log t. Zero density estimates say that there's at most t to a power smaller than 1 such zeros. So, in the strip, up to this height, there should be t log t zeros. Zero density estimates say if you move to the right of 1/2, the number of zeros is t to the something, like 1/2, t to the 1/4, whatever, depending on sigma and the estimate you prove. Okay? And those are extremely useful in proving results about prime numbers, like gaps between primes. Just one example. Another application of moments is to Levinson's result that 1/3 of the zeros of the zeta function are actually on the critical line. And you can also use moments to estimate the number of simple zeros of the zeta function. Okay, so those are just examples of applications. And here's a little bit about what we know. So I'm going to mostly focus on zeros on the moments on the critical line because that's the most difficult case. If you move away from the critical line, things tend generally to get easier. Okay, so these are the moments we're interested in on the critical line. And an estimate like this, t to the 1 plus epsilon, would follow from the Lindelof hypothesis because Lindelof hypothesis says this is t to the epsilon, raise it to a 2k power, it's t to a different epsilon, and you integrate from 0 to t. This goes the other way too. If you prove a bound like this, you've proved Lindelof. Okay, that's not as obvious. Okay, so here's some history. The Hardy and Littlewood in 1918 proved that the second moment is asymptotic to t log t. Ingham, a few years later, showed that the fourth moment has an asymptotic that looks like this. And they did this by, remember I said you use approximate functional equations to handle the zeta function in the critical strip, and that's exactly what they did. And we don't have an asymptotic formula for any k bigger than 2. In all these years, nobody's been able to prove, prove of such a thing. Okay, we do have upper and lower bounds. Maxim Radziwi, and Soundararajan, after partial results by many mathematicians over 90 years or so, prove a lower bound that looks like this. And we believe that this is the right order. Okay, so there were partial results like this where you assume RH and things like that. On RH for upper bounds, Heath-Brown was able to show that you get an upper bound t log to the k squared t for k between 0 and t, okay, and assuming RH. Radziwi, is that how you say it? Maxim showed that extended this beyond 2 a little bit. This was a really nice and interesting result. And then there was a big breakthrough in 2009 when Soundararajan proved something very close to what we think is the right order. So it's off by this epsilon here, assuming RH. So on RH you have that. And then recently, more recently, Adam Harper got rid of the epsilon. So this was really amazing. Okay, again, on RH. Okay, so it was thought, because it looked for a long time like the order was t log k squared of t. It was thought that there should be some constant. There should be an asymptotic. There is one for the second and fourth moment. So what should that constant be? And that led to a lot of work over many years by various people. Conry and Ghosh suggested that this constant, ck, actually has a structure. There's an arithmetical part, which you can write down. It's a product over primes. This is it. And there's the gamma function, and then there's this number gk, which they thought might be an integer. It is in the couple of cases we knew. So if you want to know what the ck is, what you really need to know is this gk. Okay, that's where all the mystery is. Okay, so what do we know about the gk's, or what did we know? So if you write the 2kth moment like this, then the Hardy-Littlewood asymptotic for the second moment gives you that G1 is 1. Ingham's fourth moment gives you that G2 is 2. Conry and Ghosh in the mid-90s conjectured that G3 is 42 using number theory, analytic number theory methods. And then Conry and I, in 98, conjectured that G4 is 24,024. And at the same time, John Keating and Nina Snaith were able to use random matrix theory to conjecture all the moments. So for all k bigger than minus a half. Okay, and you'll hear about that later in the week from John. Okay, so that's some of the history. And I just want to conclude, if I have like 2 minutes, I'll just conclude by telling you some of the evidence for the Riemann hypothesis. Okay, it's not all the evidence, just a few that I wrote down, and I think these are convincing to various degrees. Maybe for some people to no degree. I don't know. One is the zero density estimates I measured. That you can't have too many zeros in a strip like this. Now remember, there's a symmetry around the half line. So if there aren't many zeros there, there aren't many zeros there, and that means that the zeros that there are must cluster around the half line. Okay, and the sigma could be epsilon away, and we can prove such things, and that suggests that even if the zeros aren't on the half line, they, in some sense, do definitely cluster around the half line. So the half line is certainly special. Okay. What I think is the most arresting evidence is calculations of the zeros. There have been extensive calculations. The first 50 billion zeros of the zeta function lie on the critical line. And if you go way, way beyond that, like near the 10 to the 20th zero, and you sample millions of zeros near that, they lie on the line too. So to me, this is pretty amazing if the hypothesis falls. Calculations of zeros of other L functions have been done. No one's found, for L functions we think there is a Riemann hypothesis for nobody's ever found a counterexample. There are also estimates of the zeta function, the number of zeros on the critical line, and those are compelling. Hardy showed that there are an infinite number of zeros actually on the critical line. Hardy and Littlewood showed that the number is at least t, up to height t. Selberg showed that a positive proportion of the zeros in the box up to height t are on the line. It was an astounding feat. And then Levinson in '74 showed that a third of the zeros at least are on the critical line. And Brian Conry in '89 showed that at least 40% of the zeros are on the critical line. So, and then finally, there are finite field, function field analogs of L functions, and it turns out that in many of those cases, you can actually prove the analog of the Riemann hypothesis. Now, whether that's evidence or not is debatable, because you have all kinds of structure that you don't seem to have in the case of number fields or the rational number field. Okay, thank you.